So Venkat, please check it now.
Yes, ma'am. Yes.
Okay. Revati ma'am, can you hear me?
Ma'am, the live option is operating perfect, ma'am. No problem.
Okay, thank you. Revati ma'am, can you hear me?
Dr. Revati?
Ma'am went out and now she joined. I have given co-host to her just now. Yeah. Revati ma'am?
Yes, ma'am.
Yeah, okay, fine. I think in between you went out, right?
Yes, ma'am. That's why I was worried. Only now you have again unmuted.
Okay, ma'am. Okay, no problem.
Ma'am, can we start admitting people, ma'am?
It's already doing now.
Yeah,
It's already people are entering.
I am doing.
Okay, so, it's okay. Leave it, Venkat.
Okay.
Now you have to take photograph also, no? Immediately.
Sir,
Yes.
agenda is there, sir. We'll go with agenda. No problem.
I think a resource person has entered in the name of Department of Chemistry, ma'am. Please, can you make sure?
Yes. Department of Chemistry. Yes. Given, I think, right?
Okay, now my video is on, right?
Yes, Professor. Yes,
Yes, sir.
Professor, happy to see you after a long time.
Me too. So, can you somehow disable this admit thing coming to me also? Because this is coming in between.
You need not worry, sir, but otherwise you cannot present. Go post. No problem. We will take this admission.
No, ma'am. We can remove co-host from him, ma'am. We can present. I have given that option to him.
Okay. I'll
Because otherwise, this comes and catches my attention every time.
Okay, Professor. Okay. Yeah, I have removed the co-host permission.
That's great. So only you need to give me the share option, which multiple, that near the share screen button on the right side, there is one option.
It is done, Professor.
That if you do it,
Venkat, please take care of it.
Yes, ma'am. Already I have done.
Okay, that's because you are already sharing, something. That's why I'm not.
Yes. Now I'm sharing my screen, Professor.
Yeah. Okay, so our things. You guys started lecturing for the semester.
The last semester, end semester examinations are going to start from tomorrow. The next academic session will be start from the third week of August.
Oh, okay. We have already began our thing.
Okay. Here, based on the BTech admission, they will start the academic exams.
I came once to your college at that time that Professor Tennarasu arranged some RJSE, some coaching for this gate coaching or something. Or
Okay.
CSR exam.
CSR coaching.
That time I had been there.
Actually, one of our student is also attending, sir. Previously, we used to conduct offline in our campus. That program. Dr. Tenarasu only.
Okay. So how long you give me for lecturing?
So we'll start the session by 4:15. So just 2-3 maximum 5 to 10 minutes. The introduction part will be there. After that, you can go up to 5:30 or 5:40.
That means 1 hour you give me, right?
1 hour, 1 hour 15 minutes also you can take.
Oh, that's a lot.
1 hour is also fine, no problem.
Okay, yeah. Anyway, I will try.
Okay.
This is 1 second. I get a call.
Ma'am, shall we start the meet, ma'am? Dean, ma'am?
Dr. Asha, we can start the program 4:15.
Okay, sir. Okay, sir. Thank you. A very good evening to one and all gathered here. We hope you're all fine and doing well. And I welcome you all for this day 4 of Photovoltaics 360 design to implementation. So we believe that our webinar is going well from the past 3 days, and the participants are benefiting out of the webinar series. So these are the snapshots we have taken in the day 2 and day 3. So same way, we would like all the participants to enable their video now to take the snapshot now, please. Kindly switch on your video. Venkat?
Yes, ma'am. Yes.
Smile, please, everybody. I can see Ganapati. Good. Done?
Thank you. Yes, ma'am.
Yeah, thank you. Thank you all. Yes. Moving to today's session, we have an eminent and dynamic researcher today, Dr. R. Kodandaraman sir, Professor of Chemistry, Indian Institute of Technology, Madras, Chennai. As I have mentioned in the last day of session, Professor is my mentor for the ongoing TAR project. And I would like to share here that during this pandemic period, almost all the research laboratories are they were not able to function properly, but Professor has opened a new laboratory for energy conversion and storage related to flow batteries, supercapacitors, fuel cells, and photovoltaics related recently, and which is functioning well, non-stopping. So this indicates its dedication in research. So with this few words, I would like to hand over the session to the today's chairperson, Dr. Revati Purushothaman ma'am, Associate Professor of our department, BSACIST Institute of Science and Technology. And today's moderator is Dr. K. Shakila, Assistant Professor of our department, is alumni of IITM Chennai. So hand over the session to Revati ma'am, please.
Thank you, ma'am.
Professor Kodandaraman Ramanujam has done his MSc in Anna University in 2000 and completed his PhD in the field of solid-state chemistry unit at Indian Institute of Science, Bangalore in 2006. He has pursued 2 postdoctoral fellowships at Michigan State University, East Lansing, USA, and National Research Council of Canada, Ottawa. And now he's working as a professor in the Department of Chemistry at Indian Institute of Technology, Madras. He was a visiting professor in Energy, Environment, and Chemical Engineering Department at Washington University between April and July 2019. He is a fellow of the Royal Society of Chemistry, FRSC, and the Academy of Sciences, Chennai. He is also a guest editor for the upcoming focus issue, Energy Storage in China, in the Journal of Electrochemical Society. In addition, he is a Vice President of Indian Society of Electroanalytical Chemistry, BAC, Mumbai, for the period of 3 years up to 2024, and an adjunct faculty at National Center for Catalysis Research, IIT Madras. He is a member of the Office of Global Engagement of IIT Madras and also the member of Faculty Advisor Council of IIT Madras Research Park. He is an honorary scientific advisor for Twin Pole India Private Limited and Kapindra Precision Engineering Private Limited Research Park, IIT Madras. He is a principal investigator for the project in photovoltaic research at DST IITM Solar Energy Harnessing Center. He is a coordinator for the Center of Excellence at IITM, Advanced Energy Storage and Conversion. So far, he has obtained 12 sponsored projects and 4 consultancy projects, and notable among them is the 4 crore consultancy grant from ONGC for developing flow batteries at TRL-5. To add on to his credit, he has published 98 research articles in international peer-reviewed journals and 2 book chapters. He has obtained 1 US patent, 1 Indian patent, and applied for 5 Indian patents. Now, I am excited to invite our esteemed speaker to present on understanding the role of CDCA in tandem with Pi Spacer in DSSC. And now I hand over the session to you, sir. Thank you.
Professor, you can share your screen now, please. Professor, I have given the unmute option.
Can you hear me now?
Yes, Professor.
Great. Thank you, Revati Madam, for your kind introduction. So I hope Shakila also is here. Of course, moderator should be here. So nice seeing you, Shakila. So, and I thank also Asha for this invitation. Actually, when you said that we are taking a group photo, I was waiting for the flash. That's what we are missing in the online group photo, right? So let's.
Yes, Professor. Thank you.
So I have to keep smiling because I don't know when the flash is actually, right? Right. Good. So see what? Good afternoon to everyone, and also for the organizers. So after giving the title, I went through this brochure shared with me. So what I understand is there is a significant proportion of the audience is from students, right? So therefore, I integrated some teaching component alongside the research component in this talk. So therefore, this will not be exactly on this role of CDCA in tandem with the Pi Spacer, but there are some content related to the title, but most of them are teaching component that I have incorporated. Let me move these controls. Okay. So the inspiration for this organic solar cell comes from the well-known example, the chlorophyll. So the chlorophyll has the.
Sorry to interrupt you, Professor. The headings and all is hiding. If you put slideshow mode, it would be okay. I think so.
I also see the same thing. So.
Yes.
For me also the heading, actually there are two screens I have, so in one of them it is visible. Let me see, I can do the mirror displays. Is it okay now? Or you have seen two screens now?
Yes, we could see two screens, sir, we can see.
Yeah, so if I do the, let me see.
If it is in the view full screen mode or slide share mode, then it will go.
Let me see. Stop sharing. Is it okay now? Still I see the
The
problem.
screen is not yet shared.
The screen is shared, but when I go to full screen, I have this problem. Is it okay if I have like,
You can please share your entire screen, professor. Then you go to that particular PPT. Then.
see screen? Is this fine now?
Yes, professor. Yeah. Now if we go to the slideshow mode, then we can see the full. In view option.
Is it okay now? Let me go to the next slide. Is it okay now?
Now in the top there is a view option, no? Next to the review. Next slide.
Is it okay now?
Yes, professor. Perfect. Good. Thank you. Please go ahead.
Okay. There is a cursor and it's not coming on. Okay, let me use my cursor. Is my cursor visible?
Yes, professor.
I don't get the laser pointer coming up. So
here itself you can right click and you can get it. If you right click, you can get the pointer options.
sorry, okay. Yes. So now I think you are able to see.
Yes, professor. Thank you.
Okay, so sorry for the delay. So the well-known example is the chlorophyll, right? The chlorophyll has this porphyrin ring which can harvest the light. Okay, so it captures mostly the red and the blue part of the spectrum. So you can see here, this is the sun on top of the canopy. So this is a radiance spectra under the canopy. You can see once the light passes through the leaves, you see the reduction in the intensity, radiance in the region where the blue and red radiations are dominant, right? So that is why what you get to your eyes is only the complementary color, that is green. So you perceive the leaves as green. Yeah. So, and these are the common pigments that is present in the plant, which are responsible to harvest various part of the wavelength in the solar spectrum. And these pigments, along with the protein that is present, will help separate that excitons that is produced upon light absorption. So that oxidized part of that dye will be regenerated by water, because water undergo oxidation. So oxide ion present in the water will be converted to oxygen. Thereby the leaves during photosynthesis liberate oxygen. So this is well-known example. So we have inspiration from this, and then go to the next work. Actually, in the dye-sensitized solar cells, at the early stage, we had the metal dyes, metal-based dyes, ruthenium-based dyes were very famous. And later, people have found even metal-free dyes, which are easy to make and cheaper, as well as avenues for the molecular engineering. And most important, these dyes have a epsilon coefficient, that means extinction coefficient, which is equivalent or higher than the metal-based dyes. So these are the plus points of these metal-free dyes. Okay. So there are two classes of dies then, metal dies and metal free dies. So, but the problem is when we have this light shining on the solar cells, we are not able to capture the entire solar spectrum. Okay, so this particular tile here is basically the percentage of incident light energy versus the band gap. Okay, so when the band gap of your dye changes, you also the amount of light that you can harvest also changes. So somewhere around 1.5, you get the maximum energy harvested. Even that maximum is not the sufficiently enough, because some of the photons which are below band gap photons, the energy pertaining to those photons cannot be harvested, and those photons which has energy higher than the band gap, okay, so they are also not harvested, or if you harvest, part of the energy goes by relaxation, so there is a thermal energy that is liberated, thereby a part of that higher energy photons also not harvested, and there are other losses that are present. Therefore only this gray area is what usable as you tune the band gap of the dice. So therefore there is an optimum band gap at which you get the maximum efficiency, maximum conversion of light into electricity. And this particular plot is for the crystalline silicon solar cells. So this drawing here shows, there's a valence band and conduction band. So when you shine light, the electrons are excited from valence band to conduction band. Okay, so if it excited to some very high vibrational levels, then to the lower vibration level, it may relax by thermal route. So therefore you will miss this much of energy between this red dot to this red dot. Okay, that much of energy may be missing as heat. Okay, and then there will be a transition. Okay, and then these excitons that are produced may be separated in the external circuit, and then electrons flow in the external circuit, and you harvest the electrical energy. This is again another way of representing this. So this entire thing here, this envelope, the yellow envelope shows the irradiance spectrum or spectral power density of our solar spectrum. What we use is only a very small portion, that is the gray here. So this is for crystalline silicon single cell. Okay. So although these photons which are present here are suitable, but not all of them are absorbed. Okay, because your cell gets saturated. So only it absorbs a portion of it. The remaining goes waste, right? It's not absorbed, or it is going as heat. And then also the other end, the tail end, where the higher, post 1000 nanometer wavelength, those lights are also not absorbed. So they are not converted into electricity. There's only a very small portion that is absorbed by the silicon solar cell. So this is called the Shockley-Quasier limit. So this is about 30% for silicon solar cells. So this is not a fixed value. If you change your solar cell, the materials in your solar cell, this value will shift here a little bit this way, that way. Okay, but mostly we get about 30% is what with even with the DSSC or perovskite or with this kind of silicon solar cells. So why DSSC? Although DSSC is not as durable as silicon solar cell, but it has its own advantages. It can be very transparent, colorful, and durable. It can be made in a flexible sheet. Okay, and it is energy efficient, particularly in an indoor application, not in the outdoor application. So it can be processed by a roll-to-roll method, so that the cost can come down in processing these kind of solar cells. So this is the recent NREL chart. I am sure the previous speakers might have shown something similar to this. The one which are in purple color. So these are all multi-junction solar cells. That means more than one type of solar cells were coupled, okay, as in the layers. So these are all very expensive one to construct. So those are all currently used only in satellites and space applications, okay. But the one in blue color are the crystalline silicon solar cells. They have about 26% certified efficiency, right? The one at the bottom of the chart, these are all the organic solar cells, okay? So they have about 17 to 18% of certified efficiency. But the advantage with these guys is easy to make, whereas the one in the blue needs specialized, equipments and a clean room and so on. So the investment is huge with respect to these solar cells. So we need actually a semiconductor technology to develop this, whereas the one at the bottom are very easy. in anybody's lab, we can do this in no time. Yeah. So fabrication wise, they are very easy and they involve cheaper materials. Okay. So, but the downside is their energy harvesting efficiency is not that great. People have made with those technologies modules. Okay. So you can see here various technologies listed here. And these are the area of those solar panels that are made and tested. So let us take our dye-sensitized solar cells, which are here. So one with the gray circle around the central, red circle or red square are the organic solar cells. You can see modules up to 6,500 centimeters squared in area has been made, and then they are obtained a certified efficiency of about 11 to 12%. So that is the current status of this organic solar cell technology. You may wonder why, even though they provide very low efficiency, why are we doing? Because this can be made in multiple colors, the organic solar cells. So this can provide you aesthetic to your indoor building, at the same time harvesting the energy, so that you can build energy efficient buildings with this kind of a system. Generally, the photoanode, which is the one which harvests light, consists of a high band gap semiconductor like TiO2, which is about 3.1 electron volt. These high band gap semiconductors absorb the dye and anchor the dye by a chemical bond, as I shown here. So the donor is a part in the dye which can absorb the sunlight. It will get excited because of the sunlight, and the electron, the exciton that is produced, the electron in that exciton will flow through this pi spacer and through the acceptor because of the electronegativity gradient. So they will flow like this, those excited electrons. Finally, through this bonding, it will be injected into the conduction band of titanium dioxide. So if it has to land in the conduction band of titanium dioxide, the excited level at which electron is present should be above the conduction band of the titanium dioxide. Otherwise, injection will not be feasible, right? So the donors are of this kind: triphenylamine, carbazole, porphyrin, triisotroxin, indolin, right? The spacers can be any pi spacer like benzene, thiophene, furan, and so on, right? Acceptors, the well-known acceptor is cyanoacrylic acid. There are other acceptors like rhodanine B, pyridine, okay? So these type of acceptors are present. Generally in DSSC concern, people use also one more compound that's called quinodeoxycholic acid, abbreviated as CDCA. Okay, so this is a coadsorbent, but it's a non-photoactive coadsorbent because this also got the COH group. This can attach to TiO2 surface. Okay, so therefore this is a but it doesn't have any pi bonds. Okay, they are not visible active. Okay, so this is a non-photoactive coadsorbent. This is mainly used to avoid dye aggregation, okay, on the solid state, because otherwise these pi bonds that are present here, okay, these aromatic moiety present in the donor generally have a pi-pi interaction with the molecules. So there will be an intermolecular pi-pi interaction that will stack the molecules one over the other. But generally, if you stack the molecules or if they aggregate, you may have a quenching of excitons that is produced. That means if you are not able to separate the excitons, the electron and the hole, then you will not be able to harvest the electrical energy that is produced. Okay, therefore, it is important that aggregation is avoided, which can be carried out using CDCA. That's the advantage of this CDCA, right? Okay. And if you see the dye, when it gets excited, there are several ways by which dye gets quenched itself, or the exciton kill itself or annihilate. What are the ways? The dye can do a fluorescent emission after absorbing the sunlight, or it can undergo intersystem crossing, it can do internal conversion, intramolecular charge transfer, conformational change, proton transfer, energy transfer. There are many ways, excimer formation. So these are the methods by which dye loses energy. Okay. If you look at the schematic of this dye-sensitized solar cells, as I told you, this is an energy axis, okay, that you see here. So the conduction band is here for the TiO2, the valence band is somewhere below, and this is the dye which can absorb in the visible region. So this is a HOMO, highest occupied molecular orbital. And LUMO, that's a virtual orbital, there is no electron. When you shine light, the electron from the HOMO will be promoted to LUMO. So that you are going to see now. So you shine the light, electron goes to LUMO. The time scale involved in this process, very electron injection, excitation is very fast, a femtosecond process, very fast. And then the electron will be delivered to the conduction band. The hole will remain in the die itself. The electron will go to the conduction band of TiO2. This electron injection happens in about picoseconds range. Okay. So, and then the hole which is in the die molecule, okay, will absorb an electron from the redox electrolyte. Therefore, the die will get regenerate. Okay. The oxidized die will get regenerate. So this is a die regeneration happens in nanoseconds range. And the next step is the injected electron has to be harvested. It will come through the external circuit, which I have not shown, but you have seen the electron coming, going to the edge, and then it is returning from the right side. Okay. So that's because the external circuit it travels and comes to the counter electrode side. In the counter electrode side, generally platinum is used as a catalyst, and your electrolyte is a iodine triiodide based system. So from the counter electrode, electron will be given to iodine, that will become triiodide, and from the triiodide, electron will be given to HOMO of the oxidized die, thereby die is regenerated. Okay, so this is happening in a millisecond time scale, that electrolyte regeneration. Okay, so these are the various time scales that is involved in a dye sensitized solar cells. But you have to be very careful. What is the voltage that we get out of this cell? It is the Fermi level in conduction band of TiO2 to the redox energy level of your electrolyte, right? From where to where? From the Fermi level in the conduction band to the redox energy level of your electrolyte. That decides what is the voltage of this cell. Okay. So, but that is not the band gap of the die does not decide. So if you want the band gap of the die to decide the voltage, what you have to do? You have to bring down the LUMO as close to the conduction band. Okay. And then your redox electrolyte, you should take energy of your redox electrolyte should be taken to as close as the HOMO of your die. If you do that, then the energy gap can be increased. Okay, between the Fermi level to redox energy, which will give you the high voltage dye sensitized solar cells. Okay, and not all that, there are other issues which is unwanted. When you inject electron to the conduction band, that electron can go to the oxidized form of the die directly. It's called back electron transfer, or it can directly go to the iodine that is present in the solution, because the electrolyte is in contact with the die, right? And also TiO2. Therefore, electron can go to your electrolyte, or the electron, instead of getting injected, it can simply come back to the ground state by fluorescence or phosphorescence process. Okay, so these are the ways by which the back electron transfer happens, which is actually not good, because we can't, if this happens, we will not be able to harvest the light, because electron is not going to come in the external circuit. Therefore, this quenching or back electron transfer donation process should be avoided. Okay, so what it means, we need to design dyes whose LUMO is close to the conduction band. We need to design electrolyte whose redox energy is close to the HOMO of the dye, and we need to do a molecular architecture of the dye such that all these back electron transfers are prevented to some extent. If we can achieve these three, we'll be able to make a solar cell which is a high voltage and well performing, and able to capture most of the sun spectrum. Yeah, right. Now this slide gives a little bit of the history. Mostly the work is done on the dye part and the electrolyte part, although I see a lot of work on the counter electrode part. It is not really very important according to me, because counter electrode processors are happening at much faster anyway. Okay, and their surface area is much higher than this electrode photoanode surface area anyway. So it's not going to be a bottleneck in your entire electron transfer process. So the more concentration has to be given for the electrolyte and the photoanodes. That's what more important. That's what the many research groups, leading research groups in the world did. In 1991, it all started with the iodide, triiodide, redox couple, which is about 0.4 volt with respect to normal hydrogen electrode. Okay, so the voltage and the energy, you know, the energy of the confined orbital will be more negative, correct? So compared to the conduction band, the valence band will have more negative value. Okay, whereas if you report in terms of voltage, it become more positive value. They are opposite. You should keep that in mind. So compared to iodine triiodide, ferrocenium has 0.6 volt. That means it is even closer to, compared to iodine triiodide, ferrocene is even closer to the HOMO of the dye. Similarly, ionic liquid-based iodine triiodide systems were explored, and then cobalt bipyridine-based complexes, wherein it is even, it's almost like ferrocenium. It's about 0.56 volt, just above the ferrocenium, not below the ferrocenium. Other is copper dimethyl pyridine based complex, which is about 0.94 volt with energy. That means this is very close to the HOMO of your dye. Okay, that means if you use copper based system, you will get more voltage. That means more energy harvested. Because what is energy? Energy is the charge that is flowing multiplied by the voltage that you get in the cell. So E into V, that is energy, right? Electron volt. So more energy you can harvest only if the voltage is high. So high voltage can be obtained by copper, to some extent by cobalt, not by iodine triiodide. Let us look at the dyes. So this is the kind ruthenium-based dyes was initially shown by Professor Gressel, and those ruthenium-based dyes have some commercial names like N719, N3, dark dye, and Z907, and so on. Later on, around 2003, people have found you don't need a metal-based dye, and it's very expensive, difficult to make, and so on. So they have made some carbazole, phenothiazine, imidazole-based donors-based dyes. Okay, that's called D pi A dyes. Donor, they have a pi linker, and then there is an acceptor, and that dye molecule is attached to TiO2 semiconductor. Why do you need at all the TiO2 semiconductor? See, remember, TiO2 is a wide band gap semiconductor. Okay, the exciton is produced in the dye. If you don't have a driving force, you will not be able to separate that exciton. Then they will annihilate itself, correct? So in order to give a driving force for the separation of the exciton, we use this wide band gap semiconductor. Once the band gap goes wider, it is difficult for the annihilation to happen. So electron can be transferred to the conduction band. From there, we can harvest. Otherwise, in principle, without TiO2, you can simply have organic molecule attached to a conducting glass, and you should be able to do, but that doesn't happen because that leads to a lot of energy loss. Okay, you will not be able to harvest light. And then porphyrin-based dyes came into picture, which is mostly zinc-based system. Then again, simultaneously, research based on carbazole, porphyrin, indolin, squarene dyes were carried out. Latest is co-sensitization, because with one dye, we are not able to cover the entire solar spectrum. So therefore, combination of dyes were used, which is called co-sensitization, to harvest the entire solar spectrum and then convert that into an energy. So that's the idea. And how do we characterize these solar cells? How do we characterize these solar cells? We use commonly IV measurement, or called JV measurement. So this x-axis here is a voltage, y-axis here is a current density. Okay, whenever you shine a voltage on a solar cell, that solar cell will generate a potential because of the charge separation at the photoanode, right? So that is about typically 700 millivolt to 1 volt range, you get it. Okay, and then when you do a short circuiting, that means when you connect the circuit, electrons which are harvested in the TiO2 will be flowing through the external circuit. Okay, so this red line here is a theoretical line that shows the maximum energy that you can get. But the problem is solar cell does not perform this way, because you have other losses like IR loss. When the current flows through the circuit, it has to go through something. Even if it is a copper wire, it has a finite resistance, right? And the electrolyte ion, that iodine, triiodide ion, or cobalt ion, has to go in the solution. The solution can't freely move it. There is a resistance for its flow of ions, right? So therefore, there is a resistance. So when the current goes through this resistor, this is called internal resistance. Okay, there will be a voltage drop. That's called IR drops. So because of voltage, various voltage drops that happens in the system, we call it as overpotential. The curve is not straight like this, it is bent like this. Okay, so this green rectangle is the biggest rectangle that we can fit into this curve. Okay, so this point here is the maximum power point. How will you calculate power? Instead of doing this rectangle business, you can also take the voltage and the corresponding current, you multiply I into V is nothing but power. So you can plot power versus voltage or power versus current for every voltage that is present here. So that is the maximum power that you get. You can see this green rectangle is smaller than the red rectangle. That means the maximum energy that you can harvest must be smaller. Even it is smaller than the area under this blue line, which is the actual light harvesting, right? So because of that, the maximum energy that you can harvest, right, is much lower than the light energy that we are going to supply, right? So this equation tells you the fill factor. The fill factor is nothing but the quality of this rectangle. Suppose imagine your blue line is a perfect rectangle, then your fill factor will be 1. When it deviates from the rectangle, then the fill factor also comes down from 1. It can be 0.7, 0.8, some fraction, right? So the efficiency is nothing but the electrical power divided by the power of the light, okay, that is shining on the cell. So this power ratio is nothing but the efficiency, which is given in percentage, okay. So that tells you what fraction of the incident power of light is converted into electrical power. That's all it means. So that is efficiency, photo electron conversion efficiency. It also has another abbreviation, PCE, right? So then what should be the dye's characteristic? Dye should strongly absorb in the visible region. Perfect. We have some dyes like that. And it should strongly bind on the semiconductor because it has to make a bond with the semiconductor. If the bond is detaching, then the dye will go into the solution. Then you will not be able to inject electrons. So it should make a nice bonding with the diode surface. And the LUMO of the dye should be higher than the conduction band, but not too high. And the HOMO of the dye should be lower than the redox electrolyte, but not too low. So, and the dye has to be solution processable. Otherwise, you will not be able to absorb from the solution onto diode. And the periphery of the dye should be designed such that it is solvophobic. Because if the solvation happens to the dye, then there will be a lot of reorientation of the dye molecules when there is excitation of the electron. And also there will be electron tunneling would be an issue and so on. So that is what you should make sure dye has these qualities, okay, right? So you have seen compared to electrolyte level, HOMO should be low, compared to the conduction band level, LUMO should be high. But what is the origin of voltage loss? As I told you before, the origin of the voltage loss is one is at electron injection. Because your LUMO is above the conduction band, so this much of energy between the LUMO and the conduction band, that much of energy goes as heat. It is not shown as a potential, right? So there is a voltage loss there. That's an over potential, right? And then electron recombination, because a lot of 3 reverse process I have shown, back electron process, that will deplete the concentration of electron in the conduction band. Therefore, the conduction band energy level will go down. Therefore, that also contribute to the voltage loss. And dye regeneration loss. That means the HOMO of the dye is too low compared to the redox energy of the electrolyte. Then that gap between the electrolyte and the HOMO of the dye also wasted as heat. Okay. So we need to control these 3, right? So how do you control this voltage loss? Reduce the driving force. That means a gap between for electron injection through dye molecular engineering. That's the only way. Decrease the dye regeneration over potential through redox mediator engineering. That means electrolyte has to be redone such that the HOMO is close to the redox energy of the electrolyte. And suppress the interfacial electron recombination, that is a back electron transfer. If we take care of these 3 physics, we will be able to significantly improve the VOC by avoiding the overpotentials. Now again, there's one case study that I have given here. Okay, how they control the overpotential, thereby improve the VOC. Okay, this you can find in this paper. Okay, he has taken a Y123 dye. It's a triphenylamine based dye. The spacer here is a thiophene. Okay, and cyanoacrylic acid is the acceptor here. He has put in between a quinoxaline moiety, which is an auxiliary acceptor. That means this will interact, because this nitrogen moiety here will interact with the TiO2 surface by a non-covalent force. Therefore, electron can be injected into TiO2 through this way, or it can be injected through this way. So there are 2 paths by which electron injection is feasible. But when you add more electron acceptors in the structure, what basically happens is the LUMO of the die gets down. Okay, when it gets down, it means it's getting closer to the conduction band of your TiO2. Therefore, the over potential loss can be minimized. You can see in this IV curve, which is here with 1, 2, 3 and WS70 and WS72. WS72 gives the higher potential, higher voltage. Why? This is with iodine, I think cobalt or iodine triodide electrolyte, I don't remember, one of them. But you can see this WS72 has got a alkoxy substitution. Generally, these alkoxy substitutions are very wandering. Therefore, it doesn't allow the solvent or electrolyte to come near the surface of the dye. So, or TiO2. Therefore, the back electron transfer can be avoided. Back electron transfer avoided means the Fermi energy level in the conduction band will raise, so that you will get a higher open circuit potential. That's what you see in this IV curve, basically. Now, let's look at the another example. What they have done instead of, okay, the previous one was with the cobalt electrolyte. So instead of cobalt electrolyte, they have used copper tetramethylpyridine based electrolyte. Okay. Why? Because this gives only 0.56 volt, whereas this gives 0.87, nearly 200 or 300 millivolt higher. So therefore, the cell which was giving 0.7 volt, if you add this 300 millivolt to that, it will give you 1 volt. That's the idea here, right? So you can see here the corresponding IV curve. You can see as you modify from white 1232 quinoxaline modified dyes, there is an increase in open circuit potential. That's what we need clearly. So what we have done, we have put quinoxaline and brought down the LUMO close to the conduction band. So we reduced one over potential, and then we manipulated your electrolyte and brought the redox energy close to the HOMO of the dye. Another over potential is controlled. So therefore, you have increased the open circuit potential. That is what you should keep in mind. And if you look at, one more aspect that we have not discussed is the back electron transfer. Okay, that means the recombination kinetics. When the electron is injected to conduction band, it can directly come to the oxidized dye, or the dye itself can lose the excitons by direct, fluorescence or phosphorescence process. How do you understand this back electron transfer rate? Okay, how fast is this back electron transfer? To do that, we need a technique called flash photolysis. Okay, this is also called in a textbook pump probe technique. Okay, but we call that as a transient absorption spectroscopy. Okay, transient absorption spectroscopy looks more technical. Okay, so what is pump probe technique? Basically, we have a sample that it may be dye. Okay, and there is a pump pulse which is given to this sample. When the pump pulse comes, it's a laser light. Okay, so all the absorption spectroscopy, right? UV visible absorption spectroscopy. What happens when the light shine? Molecules get excited. Same happens here. When the pump source comes in, the molecules are excited to a higher energy level. After some delay, we give another pulse, which is a probe pulse. The probe pulse will actually monitor. Okay, it will monitor the excited sample, because when the pump pulse enters, significant percentage of the molecule has already gone to the excited state. Okay, which will reduce the epsilon, that is absorption coefficient, for the probe pulse. Because when the probe pulse enters the sample, most of the molecule is in the excited state. So therefore, there is not enough molecule in the ground state to pick the light that is coming from the probe pulse. So which can be technically called like this: the absorption coefficient or cross section, which is epsilon value, now decreased for the probe pulse. Okay, so that's what we are going to monitor here, but we do this probe pulse at a different delay time. Okay, so how it is done? So we have a pump pulse which enters the sample, goes somewhere out, and then probe pulse which comes after a certain time delay and sees what fraction of the molecule is excited, and different delay tells you what fraction comes back to to the ground state and so on. Because when you wait too long, the molecules which are excited will come to the ground state, so that when you send the probe pulse, you will have a huge absorption. Okay, so that will vary with the time, because the excited state particles coming to the ground state. And this probe light will go to the dispersive element, like a monochromator kind of a thing. So it will separate into multiple wavelengths and then go to the detector. We can also do the probe pulse at monochromatic light or at white light, the way we want. So how it actually works, it's a femtosecond transition absorption spectroscopy. We have a laser, the laser beam gets split into two parts. One is pump part, another is a probe pulse. The pump part goes and enters the sample directly. Okay, during that process, excitation of the molecules happens. The probe pulse goes through a circuitous route. So it goes through some many kilometers of distance. Okay. So when it does that, travel, it will get delayed. When you increase the traveling path, the delay will be even more, right? So by controlling this delay stage, we can delay the time or the time gap between the pump and the probe. Okay. So that's the delay stage. This can be varied so that light can be asked to go to a longer distance or shorter distance. And then it comes this way and enters the sample again. And then it monitors the, how many dyes are there in the ground state, so on. So that is what sent to the detector and we see a spectra. That's nothing but an absorption spectra basically. This is a facility that we have at IIT Madras, femtosecond TA instruments facility. And you can see at time 0, okay. So this is my absorption spectra, okay. When time t means after certain delay, when significant portion of your molecules gone to the excited state, that time when you do an absorption spectra again using the probe pulse, that time this is the absorption spectra. The intensity is naturally lower because less number of ground state particles are there. So if you take a different spectra between these two, because this is small and this is bigger in value, so you get a negative absorption delta A. Okay, this means the ground state is bleached. Okay, so the delta A versus time. Okay, we can also plot delta A at this is at particular time. Okay, delta A at one time, but we can do this experiment at different delays. Okay, so we can calculate delta A for each wavelength for a different time, right? So that is what TA spectra. So if you look at it, this is a transient absorption measurement, and we use basically a Beer-Lambert's law here. Okay, so we have a probe pulse which is having multiple wavelengths and so on, which is detected, and this is how this your spectra looks. Transient absorption spectra looks for different delay times. Different delay time. What is the delay? The delay between the pump and probe pulse. Okay, so we can choose any particular wavelength and plot the delta A value here with respect to this delay time. Okay, if you do that, you get this particular curve which are here. Okay, delta A versus different time delays. Now you can fit it, this curve. This looks like for me a first order reaction, right, where concentration changes with the time like a exponential fashion. So if you fit this curve, okay, with appropriate equation, you get a time constant. That time constant talks about the recombination time, how fast the exciton undergoes recombination. Okay, so that tells me about the recombination time. That time should be longer. That means it should take longer to recombine. Therefore, it is available for injection into the conduction band. Otherwise, it will not be available for the injection. Okay, that is the criteria. Now, the same person has done this experiment using a DSSC cell, but in the electrolyte, instead of iodine triiodide, he has used an inert electrolyte. That means there is no redox reaction possible there. That means the electron from the conduction band of TiO2 cannot go to the electrolyte because there is no iodine triiodide, whereas it can go to the oxidized dye. So we can basically calculate in this fashion the recombination rate of between the electron in the conduction band to the oxidized dye. So he has calculated for Y123, WS70 and 72. This is 4.5 millisecond, 9.5 millisecond, and 13 millisecond respectively. That means what? WS72 has got higher recombination time. That means it is slow in recombining. More time it stays in the excited state. So it is useful because it can be injected into the conduction band easily, right? So that's the idea. So that's what that molecular design has achieved. What is the molecular design here? If you see carefully, once again, let's go here. You see this fellow quinaxolone, when you put the recombination time is increased to 9.5 millisecond. But when you attach this alkoxy substitution, it further increases. That means this alkoxy substitution delays somehow the recombination of electron in the TiO2 to the oxidized dye molecule. Okay, so that is called molecular engineering. So we do some changes in the structure so that we get the desired property. That's called molecular engineering. See, Yeah. Now let's go back to the slide where we were. And what the same person did, he did something interesting, which I liked it actually. He used what do you call the copper electrolyte, which is copper tetramethyl bipiridine. Remember that copper electrolyte has been used, okay, but it was first a TiO2 layer, then you absorb the dye on it, and that you drop this copper electrolyte and evaporate the solvent. Therefore, a thin layer of copper electrolyte will be coated on your dye TiO2 substrate. Okay, it should not be too much, it should be not too thin, too thick also. Okay, and then you place a counter electrode on top of it by physical vapor deposition or some method, right? So, and if you look at it, it will look like this. You have a TiO2 transparent layer and TiO2 scattering layer. You know why scattering layer used? Scattering layer actually because these are the particles which are of the size of the the wavelength of visible light. So what happens when the light enters from the bottom of the glass, and it will get scattered by this layer, the particles, TiO2 particles that are present here. So when it gets scattered, it may return in the same path like this. Okay. So once it goes incoming light goes this way, the scattered light goes in an angle or multiple sides, right? Multiple times it makes a trip within this layer. Okay. Therefore, the chance of the light seeing the dye is increased. Therefore, the probability of light absorption can go up. That is the advantage of this scattering layer. But it doesn't absorb any dye because this is low surface area layer compared to this transparent TiO2 layer here. So dye mainly get absorbed in this layer, and this layer mainly makes multiple excursion of the light into this matrix. And then we have this whole transport material, which is nothing but the electrolyte. Because why electrolyte is called whole transporting layer? Because electrolyte donates electron to the dye that is present here, okay, and accepts the whole. By giving electron, you means you are accepting whole, right? That's why it's called whole transporting layer. And the electron travels to the TiO2, go to the ITO glass here, and then it comes this way doing an electrical work outside. Okay, so this person has done this at a variety of suns. 1 sun, 0.64 sun means they reduce the intensity of light falling on the sample, right? 0.5 sun and so on. And he has shown here the IV curve at a different sun. This is at 1 sun, 8.5% sun means almost 1 sun. And as you decrease the intensity, obviously the current density will drop because less light is going into the sample, less electrons will be generated, so less electrons flows in the circuit. So current density obviously will be less, but not much change in the open circuit potential. And as you can see, as you go reduce the sun value and then finally reach the dark condition. So this is basically the dark electron transfer, right? That means when there is no light shined, when you apply a bias, what kind of current you see? You don't see any current in this region. Only when you cross this band gap value, then you'll be able to inject electron in the semiconductor. So that's the current that you see here, right? Right. So this cell is also called as a zombie cell. Zombie, it is a dead person being alive, right? Something like that. So initially the people thought when we use this electrolyte and coat it on it without any solution in that, then it may not work. It will be like a dead cell because electron transfer, whole transfer may not happen well and so on. But surprisingly, it worked, and in fact, it gives a higher performance too. So therefore, it is called as a zombie cell. Just this thing. So and then I would like to show here why DSSC is a preferred choice for the indoor use. Indoor use means within the house or within the office and so on. So this paper had this particular information wherein XY1 dye. Okay, it's basically a triphenylamine dye, and then a 5T dye, which has a 5-thiophene with the alkyl substitutions with the cyanoacid acid. Okay, these two are mixed. This is very cheap dye. Okay, these two are mixed in certain proportion, and then this IPC means incident photon to current conversion. This is also a kind of your absorption spectra. Okay, it's called IPC spectra. Internal quantum efficiency is kind of calculated using this. So if you see the IPC percentage with this wavelength, higher the percentage means most of the light is absorbed. That's what it means. So between this wavelength to about 700 nanometer, there is a panchromatic absorption. Okay, so these two dyes together, called co-absorption or co-staining, helps us to harvest more light. You can see here, this is an absorption spectrum. Only XY1 is here, and the phi t is here, the combination is here, but there is some gain in this region for the combination dye. Okay, the area under this blue line in the region is more. That means higher wavelength region. Okay, so that kind of helps to harvest the entire light spectrum and improve the performance up to 9.53%. But if the sun light is decreased, that means we decrease, what it means technically is we are going from outdoor to indoor condition. Okay, 1000 lux and all you get with the 2-3 tube lights, correct? So you go from the bright sunny condition to indoor condition, you could see more fraction of the light has been captured, because the indoor light will have more of this blue light. Okay, right? So you might have seen some blue, carefully we will observe our tube lights here, the blue tinge in that, right? So therefore, since the spectrum itself is changing, the available wavelengths and the number of photons at each wavelength is changing, the percentage of conversion of light to electricity goes up significantly. 3 times it has gone up. Therefore, I am saying DSS is a very good choice for indoor application. This will harvest better in the indoor condition. Yeah. And I am reporting here some of the best dyes reported in the literature at various times. Around 2000, these are the ruthenium dyes which were ruling the DSSC. And later comes, 10 years later, the porphyrin dyes, very interesting. And then porphyrin dyes itself has very many varieties. They gone up to 13%. And these are all the other class of dyes which had also shown a good percentage of efficiency. So with both metal and metal-free dyes were almost same in terms of efficiency. So here I am going to give another story. You see here, this is a zinc porphyrin, has got some biphenylamine kind of a substitution here with an alkoxy substituent here. And this is replaced with the biphenylamine substitution and then fluorine. So fluorine substitution instead of the biphenyl substitution. These are the variety of substitution that is. Why did they do it? If you look at this recombination resistance is lower for this dye, whereas it's higher for this. Recombination resistance higher means it is difficult to undergo recombination. That means back electron transfer. So that R value should be higher. We prefer it should be higher, right? And VOC, you see, when that is going higher, your VOC also goes higher, and also JSC. What happens? Let us look at these fragments and their invisible spectra. So this is a diphenylamine moiety that has got a Sarad band here, and there are some Q bands here. And this red one is a biphenylamine moiety, right? And then this is a fluorine-based molecule. The fluorine-based molecule has got another band here, okay? So same thing happens. Here I have plotted the entire dye. Here only the fragments, intermediates. Here the entire dye, this SGT20, 315 and SGT21. So you can see the extra absorption of light somewhere here. Okay. But including this alkoxy group here kind of twist the molecule basically. Therefore, in that molecule, there is a blue shifting that you can observe here. Okay. So now let's go to another class of dye. Okay, here what we are doing, we are keeping this thieno-indole part constant. This is a thieno-indole part. Okay, and then modifying the substitution here. Is a biphenyl with alkoxy substituent, biphenylamine. Here fluorine substitution, and here substituted fluorine, alkoxy substituted fluorine, right? Here again, the chain length of the alkoxy is changed. And here an alkoxy with a fluorine with a alkoxy phenyl substituent. Basically, we are making the donor side, very bulky and to create a steric effect. Okay. So when we do that, what happens? Since you have fluorine, you have this band here. Okay. You can see there's additional light being harvested here. And this fluorine somehow improves this VOC, the open circuit potential, because basically it cuts down from our previous light photolysis study, we understand. It cuts down the back electron donation. Therefore, the VOC has increased, JSC also has increased. okay, because now electrons are available to flow in the external circuit without undergoing recombination, right? So if you look at carefully, the VOC, JAC goes up as you go from this green one to the red one, which has got a longer alkoxy chain, from there to the phenyl alkoxy modified fluorinone. So as you may not be able to see, there is a line here which shows a VOC, JAC going up, okay? So now the fluorine substitution on the triphenylamine seems to be an interesting way to reduce the recombination, okay? So that means over potential later the recombination will go down. Now there is a combination of two dyes. You take the zinc porphyrin dye, put the fluorine, so that fluorine will reduce the recombination rate. Therefore, electrons are available for the external to flow in the external circuit. Combine it with another metal-free dye. There also you put fluorine. So same property can be imported here too, right? How much time I have? Yeah. So now, if you combine these two dyes and look at what is the performance. This is with the cobalt electrolyte, which is about 0.56 volt with respect to NHE. And this one, I think, with copper iodine electrolyte. Yeah, this is with iodine triiodide electrolyte. So as we expect, with the cobalt electrolyte, open circuit should be higher. Why? Because your redox energy of the electrolyte close to the home of the dye. So you gain some voltage there. And then what happens to JAC? It's also improving. And what happens to the efficiency? Efficiency also has improved. What happened to the recombination resistance? Recombination has to be higher because we have recombination resistance in principle should not have not changed because there is same combination of dye we are using, but the local environment is different because of the electrolyte that we have. Therefore, there will be a change. So there is an increase in that is beneficial further. So therefore, you see, this is the SGT 149 dye, which is the blue one here, and SGT 021 dye, which is a metal-based dye you see here. Okay. So together they kind of cover the entire solar spectrum from 300 to 800 nanometer. Therefore, more light can be harvested. You see the short circuit current density, generally it is around 15 milliampere per centimeter square. It has gone up to 20-22 milliampere per centimeter square. And the voltage with the cobalt electrolyte has gone near 0.9 volt for these particular dyes. That's very interesting. So we have learned three strategies by molecular engineering. What is the three strategy? Manipulate the LUMO of your dye such that it is close to the conduction band of TiO2. Manipulate your electrolyte redox energy such that it is close to the home of the dye. And manipulate the back electron transfer rate by doing these decorations. Okay, the main part here, donor, is only this. All this here is a decoration, which is mainly to prevent that electron transfer. I mean, recombination reaction. So these are three strategies which you need for this. So all these dye molecules they have done, their recombination resistance is going up when they do this modification, JSC and VOC and so on. If you are interested, you can go through this paper. And another example for the co-sensitization. Here, a triphenylamine with fused thiophene and cyanoacetylenic acids acceptor is taken, which is called leg 4, and ADEKA1, this is here, which is like a 5 thiophene type of molecule, but with a carbazole donor attached to one end and a silyl-based acceptor in the other side for anchoring. This particular dye gave about 11.2% of efficiency when you use iodine triiodide, okay, and it has gone all the way to 14.3% when you use cobalt-based electrolyte and a gold-based and graphene nano platelet-based counter electrode. Okay, so you can see their corresponding absorption spectrum and also the IV performance here. And now I enter into the research that we do in our laboratory. So Divya has made these molecules. This is a pyrene, is a good electron-rich compound, and this is a cyanoacetylenic acceptor. And she has introduced a carbazole, alkyl substitute carbazole in between, with a linkage of single bond and with a linkage of double bond here. What we kind of generally observed is, and she has also made a device with these dyes, including CDCA, which is a anti-aggregator, right? So that is used, co-adsorbent, photo non-active co-adsorbent. So what we find is whenever we have a spacer like this, the performance goes up with the CDCA. Okay. Otherwise, with the CDCA, performance goes down whenever you don't have a spacer. That's what we were seeing in this molecule. At the time, we were not sure why this is happening with this molecule, why there is a decrease in performance. Generally, literature says with the CDCA, performance goes up, but it is not. So, but here in this case, when you include CDCA, the die loading comes down also heavily in all the cases. That is one reason why less conversion happens. But at the same time, you are preventing the quenching, therefore there should be improvement in performance. Okay. So subsequently, she has made a die and she named it as a star burst dice. Looks like a star bursting. So here you can see carbazole, triphenylamine, and phenothiazine based, donors. Okay, and this phenothiazine based one performed better. So she introduced a linker in between. The linker can be just a benzene type of pi linker or thiophene or furan and so on, right? So she has introduced this linker to understand its performance. When she did the DSSC with and without CDCA, that is, anti-aggregator, right? So these are the dies, CCIM, TPIM, PZIM. These are the ones which doesn't have a pi spacer, right? With that, if you add CDCA, what happens is the power conversion efficiency goes down. See, compared to all the green bars, the red bars are at lower efficiency. It goes down. Why it is going down? If you look at carefully, the JSC also is going down for those 3 cases. Also, the VOC die loading also goes down. Okay, so all these contributing to lower performance of the die. But when she include a spacer like benzene, thiophene, and furan, and then add CDCA, there is an increment in the performance. Why it is increasing? You can see here JAC has gone up, VOC has gone up. Also, your die loading is not as low as this guy here, but there is a decrease in die loading always. Okay, but it seems the gain we get due to anti-aggregation is better than the loss we have due to die loading reduction. Okay, we see that here. So what we understand is the CDCA needs some kind of some amount of space, because it's a very big molecule. There will be a steric effect when it goes between the die molecule. There should be some room to accommodate the CDCA. Then only it can do that. When it co-adsorb, it can do very well this anti-aggregation business, so that you get a better efficiency in the solar cell. So that is what the crux of this study. And this shows the photovoltaic parameters. Those who want to see in detail, you can see here. This is a VOC. There is no change in VOC, but whereas in this case, there's a significant change in the VOC when you have a spacer like furan, thiophene, and so on. Also, the short circuit current density goes up, and also your efficiency that goes up. So these are the corresponding IV curves. Here, what we did subsequently, Jagdishwari and Ganapati, is we thought of doing a process by which this electrosorption, okay, that's called electrosorption. We wanted to increase the die loading on the electrode in some ordered fashion. So we have taken N709 and also 2 metal-free dies. What we are basically doing is by applying a potential to the titanium-coated electrode photoanode. Okay, so by applying a potential, we basically disturb this equilibrium. So this is the carboxylic acid group coming from the die. This OH group that is present on the TiO2 interacts with this, forms a esterification reaction, right? So this equilibrium can be manipulated by applying a potential to this surface. That's what we have done here. Therefore, if I make this equilibrium goes towards right, I will form more of this esterification. Therefore, more dies can be anchored on the TiO2 surface. So that's what they have done. And we could see within 1 hour, we are able to, this actually is not, this is a conventional method. In conventional method, it takes about 12 hours to get completely dyed the TiO2 surface. Whereas by this potential application method, within 1 hour, we can coat the entire die on the TiO2 surface. Okay, that's the idea here. So this is how this process happens when you apply potential. And these are the 4 dies he has used for this application. One carbazole based, triphenylamine based, two metal dies N709 and Z907. Okay, so these are the potential that has been employed for absorption of the dye on the TiO2, right? So you can see this is the absorption spectra with wavelength. This C represents the conventional dyeing process. Okay, whenever you don't have a C, then it is called a electroabsorption process. Okay, so N represents the N709 and Z represents Z907 dye. Okay, as you could see, whenever we do by electroabsorption process, the absorption is higher. That means more dye gets onto the surface. Therefore, more light harvesting can happen. Correct? So you can see this performance here. Compared to the black one, the red one has significantly improved performance in terms of JSC. That means the back electron transfer is kind of prevented because the VOC did not improve much, but JSC has improved. So the back electron transfer did not happen much when we use the electroabsorption process, because that will dictate how the dye absorbed and how much dye absorbed and so on, right? And this table shows, we have made several cells and take a champion cells efficiency here. The average cell efficiency is given here from the 5 cells. In all the cases, you can see whenever we have electroabsorption, see the second one is electroabsorption, the first one is conventional, okay? Whenever we have electroabsorption, we are able to increase the dye loading. This value multiplied by 10 power minus 7 mole per centimeter square. And then when in all the cases you see there is an increase in the dye loading. Therefore, there is an increase in the performance of the cell. And here we are showing the impedance spectra recorded in presence of light on these dye sensitized solar cells. It typically shows two semicircles. The first one belongs to what do you call that, the counter electrode reaction. The second one is belong to the photoanode reaction that is happening here. That means recombination or the electron injection, all this process put together here. So you see here, this is the solution resistance, and there's an RQ parallel combination is adapted for the counter electrode, and counter electrode is in series with your photoanode. So therefore, I connected in series another RC, which is for photoanode. So instead of C, I used Q here. Q is nothing but a leaky capacitor. This is basically a capacitance, but not really a EDLC type of capacitor. Okay, so this is RQ1, R2, Q2. This belongs to the counter electrode, and this part belongs to the photoanode. So we have fitted our data with that. We could see the solution resistance is not much of a different because it's all of them using iodine triiodide electrolyte, whereas the R1 value, which is for counter electrode, is also not very different. The R2, which is responsible for the photoanode, so there is a significant increase in the R2 whenever we do the dye coating by electroabsorption process. Okay, so that means R value increases, that means R recombination value increases, means what? The resistance goes up for the recombination, so recombination is reduced. That's what I see in every case here. There is an increase at least 2 times. Okay, so and then you can also see the tau n is the electron lifetime. Electron lifetime goes from 43 millisecond to 51 millisecond. Remember, in the previous experiment where I showed the laser photolysis, we have done the electron lifetime calculation without using iodine triiodide. We had only the electrolyte without that, right? Inert electrolyte. Whereas here we have electrolyte, okay, containing iodine triiodide. Okay, so that means there are 2 channels by which electron recombination happen. One is from the conduction band to the oxidized form of the dye. Another is from the conduction band to directly to the electrolyte. Okay, so this tau value you see may be sum of those 2, a combination of those 2. So as you can see, the tau n value goes up. What it means? The electron lifetime is higher. That means lesser recombination. That's what happens in each case if you see carefully. So between the electroabsorption case and the conventional absorption case. And this is the transport time. Transport time means how much time it takes for the electron to transport across the TiO2 layer. And the transport time decreases. Transport time should decrease because if the electron sits in the TiO2 layer for long, there's a chance for recombination. So therefore, we have to, it should be quickly transported. So that should decrease, and it is decreasing. So therefore, there is an improvement in the efficiency. This is the charge collection efficiency that goes up as you do these changes. How do you calculate these quantities tau n, tau s, and eta cc charge collection efficiency using the impedance spectrum? Very simple. From all these 5 parameters that we have is what used in calculating these 3 parameters which are here. If you look at carefully, Q2 is a constant phase element, is expressed in this U. This is nothing but the admittance. So it's expressed in the unit of mho seconds power fraction n. Okay. So if you look at carefully, the C2 is linked to this admittance and the resistance R2, which is the photoelectrodes recombination resistance, right? In this fashion. Now, because C2 is dependent on 1, 2, 3 parameters, so there will be, when you calculate C2, errors will be contributed by these 3 parameters. So how do you calculate the total error? The total error in C2 is error from the Y2, which is admittance component, error from the R, which is the photoanode recombination resistance component, and N, which is a constant, which is less than 1, which is used in this Q2 calculation. So then we can do this simple mathematical conversion for differentiating this C2 equation, substituting here, right? You have to take this C2 equation, substitute it here, and differentiate it with respect to Y, R, and N. Then you end up something like this. This gives you a total error for the C2. Yeah. So many people in the literature don't give this detailed table. Here you can see we have also given the chi-square. Chi-square is the goodness of fitting. Okay, so the goodness of fitting has to be as low as possible, should be 0, right? So then only it is a very good fit, and you can see these lines which are going through the circles are our fit to the experimental data, which is those squares and circles are experimental data, and the lines are our fit. You can see the very good fit between the experimental and the theoretical data, and that is reflecting in the chi-square value, which is very low. And then we can calculate tau s, which is a transport time, which for that you need to multiply the solution resistance to the C2, which is a capacitance arising from the Q2 value of your photoanode, and then tau n, which is a lifetime, for which you to take the R2 value of your TiO2, photoanode, and C2 value. So these time constants are calculated from this, and also your NCC, charge correction efficiency, depends on RS and R2 in this fashion. Again, the same thing. The tau s depends on 2 parameters, so differentiate between with these 2, and then calculate the total error. Same for here and same for here. So you do that, you end up these equations which I've shown here to populate the previous table. And this work, which is the last one I will discuss, this is done by your madam, Dr. Asha Joshni, through the TAIR fellowship. She is very studious, despite all her work in that place, and IIT from Abdul Rahman traveling itself takes a long time. But I appreciate her patience and passion. She worked with my postdoc, Dr. Jagdishwari, and created this. So initially I was skeptical, but I liked this approach slowly, because although it is a crude technique, for example, she uses a lot of carbon containing material, does the pyrolysis. The problem is in pyrolysis, you don't know what is happening, what is forming, some black thing forms. But she has put her mind here. She took this material, did some dialysis, and selected carbon nano materials of particular size. I think 1 to 4 nanometer size, very selective. Okay, you get a big carbon mass, but she selectively removed only the carbon nano dots of this size. That she incorporated into the TiO2 layer. The interesting thing, when you incorporate that into TiO2 layer and fire the TiO2 at furnace, that CNM, which is the carbon nano particles, will burn in air. When they leave, it will cause some porosity in the TiO2 surface. Therefore, the surface area of the TiO2 layer will increase. So more dyes will be absorbed, okay, and more electron transport can happen, electrolyte transport can happen. So this should eventually raise the performance of the solar cell. That's what happened. This is N709 dye, commercial dye, with and without the CNM. We could see there is an improvement when you simply add 0.58%. Too much you add, it doesn't work. Just 0.58% she added, and the performance jumps from something like 7%, which is for this commercial dye, to 10%. So same dye, same TiO2, just a magic, a small amount of 0.5% of CNM she added. So I think she published here as a corresponding author. So this something I like the way it come out. And to the conclusions, what for DSSC, it cannot be used in the outdoor application. It is good for indoor use. It can be considered as a replacement for the primary battery that we use at home. And solid state DSSC, like a zombie cell, is a way forward because there's no liquid thing in that. So, and it will be more stable. Therefore, is expected to be stable compared to this, and its performance also close to the liquid one. And here I wanted to show particularly Asha Joshini wanted this. So this is a video on the facilities that we have at IIT Madras, and you are all welcome to use that. We have a good idea. Okay. Okay. Now, sorry about it. So basically, we had a ITO glass plate. On that, by screen printing, we did the coating of TiO2, transparent layer, and then a scattering layer, which was put in a dye bath, and dye was absorbed. And simultaneously, we prepared a counter electrode, drilling a hole. So we sandwiched the two cells by UV curable paste, and then an electrolyte was filled through the hole and then sealed again. The cell was ready for the testing. So, and at the end, okay, almost I'm at the end. This is the acknowledgement section. So those who are working in the energy storage like me, they like this plot. This is called Ragoon plot. Ragoon plot is a plot of energy density versus power density. And fuel cells, they are energy dense, but their delivery of energy is poor. Okay, therefore it's less in power density. Whereas capacitors, if you take, their energy is not dense because they have only limited amount of surface area, and that they store the charge under the potential gradient. But they can deliver the charge quickly or energy quickly. Delivering energy quickly is called power. So they are very good powerful device. They are energy density device. So all the people working in this area of research want to go in this direction where the arrow points, where you have more energy and you deliver that energy very quickly. So that is what my student does. They are very good in, they are bubbling with energy and they are able to deliver quickly, disseminate the results quickly. So I thank all these students. This is a very old picture because of Corona 2 years. I have not seen my own students sometimes, right? Some of them are hiding themselves. But anyway, so this is very nice. Then I thank you all for your attention. I'm happy to take if you have any questions. Yeah.
Thank you so much, Professor. It's actually a very wonderful session. You have the time management also you have done really well. I hand over the session to the today's moderator, Dr. K. Shakila, ma'am.
Yes,
Please,
Shakila.
Good evening, sir. How are you?
Very good. How are you?
Oh, fine, sir. Thank you. It's been a long time.
Yeah.
Yes, sir. Yes, sir. It was really very wonderful, sir. As usual, like always, you have today also you have delivered a very energetic talk. It's all about energy, and your presentation was very energetic, very informative.
Yes.
When you started
Actually,
with, yes, sir.
I am actually missing, drilling you guys in the Viva OC or
Yes, sir. I was your DC student. You were my DC member.
Yeah.
Yes, sir.
Yeah. Okay, good. Glad that you are there. And
yes, sir. Sometime soon I want to meet you. I didn't come to campus so far. I'll come once.
Sure, definitely.
Yeah. Yes, sir. Yeah, today's your presentation was really wonderful. I definitely know all the participants have enjoyed it. So you have started with the class of dyes for the DSSC and then its advantages as aesthetic value. And then you have also discussed various components of DSSC. That is very, very important to understand right from the basics. And then device efficiency measurement through JV curve, you have explained beautifully in detail. You have discussed every step in that. And you have also introduced a new thing, that is an advanced technique, that transient absorption spectroscopy for analyzing this process of DSSC. So that is also very, very interesting we find. And also this whole transporting material, zombie cells you have discussed. So that is one thing we liked a lot. And then co-sensitization and starburst dyes. Which
you like it because it's zombie?
Yeah, it's written zombie cells. It's a whole transporting material in that. Yeah.
Great.
Okay, and yeah, you have also discussed this electrosorption, sir, where the dye loading can be increased. So that is also very informative. And then finally, this virtual photovoltaics lab tour, which you have taken us. So I'm pretty sure that all our participants would once want to come there and then have some experience there.
Sure. All my facilities are open. If you have a good idea, we can always do like the way Asha has done. Yeah.
Yes. She is one of our most favorite researcher in our department. Yes, sir. Now I request all the participants to unmute yourself, and then you can ask questions if you have any. You can ask anything on the slide or from the basics, anything.
Yeah, Venkat, please enable the participants' audio enable.
Participants, please go ahead.
Good evening, sir.
Yes, good evening.
This is Srinivasan from Presidency College.
Yes, sir.
Now, nowadays, people are using natural dyes in dye sensitized solar cell. What is your comment on it?
See,
it is better than.
Yeah, go ahead.
It is better than what you have mentioned. So many variety of dyes.
See, if you look at carefully, see, you take lessons from nature, right?
Yeah.
So you still see my slide, I hope. So if you see the nature, what it does not depend on one dye. It is also using 3-4 pigments together, okay? So, and then makes the its own dye sensitized solar cell to make its food and oxygen for us. So that is what we are also heading to now. We are doing a core sensitization. There's nothing wrong in extracting dyes from the nature. All you need to worry about is how cheaper it is to extract from the plant source or some other source, and how pure it is, right? So if you are able to extract in pure in large quantities and so on, that can be one added value to the agriculture product. Yeah. So yeah, but I can't say whether it is good or bad. It all depends on the cost involved in extracting those materials. And once after extraction, you have to study their photoaction spectra, and only if it is suitable we can use. Otherwise, we cannot.
Okay. Then the next one is, if I am synthesizing a new molecule, how I can calculate the HOMO and LUMO values of that material by experimental?
You can combine the cyclic voltammetry to the UV visible spectra. Okay, the UV spectra tells you energy required to go from the HOMO to LUMO, correct?
Yeah, gap, energy gap.
Yes, but your cyclic voltammetry tells you energy required to remove electron from HOMO. Okay.
Okay.
Because when you cycle, when there is an oxidation of the dye, it means that is a point where the dye is giving out electron. Okay. From that potential, you will understand what is the energy required to pull the electron from the HOMO. Right? Potential can be converted to energy easily. Okay, because you know delta G is equal to minus NFE. So from the relation, potential can be turned into energy. So now you know the HOMO energy from cyclic voltammetry. To that you add the lambda max, which you can convert again to energy, and add that energy. That should tell you where your LUMO is located. Correct?
Yeah.
That is how. Or you can do some photoelectron spectroscopies. Yeah, that's another possibility. But in the laboratory we do using CV.
So okay. And the next one is, if I am synthesizing TiO2 material, if I have any defects present in oxide material, whether the performance of the solar cell will improve or it will degrade, sir?
Generally, in my opinion, if you introduce a defects and all, it will decrease only. Although I see a lot of reports which is boosting this, that, all that, maybe under certain circumstances, yes, but not always, because when you introduce defects, you are basically introducing, if you see this figure here, okay, you are basically introducing new levels between the conduction band and the valency band, correct?
Yes.
So those new defect levels may trap your electron, okay? Yeah. Or may help you to do the better electron injection. We don't know that. A lot of physics involved in that. You need to do a detailed study and then decide whether to use that particular defective material or not. But in general, if you introduce too many defects, it may be counterproductive.
Okay. Yeah. And last question. When you look at the energy gap value itself, we can predict the excited state lifetime. If you are using additionally with TA spectroscopy, is there any advantage over that this conventional?
How can you predict the time from the band gap? You can't.
Yeah, according to Heisenberg principle, delta E into delta T is equal to almost h by 2 pi value. If you reduce the delta E, that is the energy gap value, automatically the delta T will be large. That is why the recombinations.
That delta T nothing to do with your, recombination lifetime and so on, right? Oh. But still your electron is in the bound state. You are going from one bound state to another bound state. This is like a transition, okay? Oh. So that means the electron literally goes from a different molecular orbital to another orbital, okay? So that delta T is, you can't use it here, okay? Oh. If you want to use, you have to use some corrections, then yes. Oh. But otherwise, this is the one method, or impedance is another method. Flash photolysis and impedance are the methods by which you can do. Yeah.
Thank you, sir.
Yeah.
Yes. Any more participants?
Good evening, sir. Sir, can you explain once more why actual curve is deviated from the theoretical curve, that IV curve? You told that yeah. Yes, sir. Yes, sir.
Yeah. See,
yes.
If you see, this is the actual curve, correct?
Yes, sir. Yes, sir.
I don't have pen, otherwise I would have written to you. The thing is,
yes,
when you have a battery or any solar cells, whatever it is,
yes,
you have an electrode and there are electrical connection to it, correct?
Yes, sir.
So every junction has got a resistance, contact resistance.
Yes, sir.
And even if you consider your copper wire is good conducting, but still it has some finite resistance.
Yes, sir.
So therefore, when you apply a voltage, say for example, you have a total resistance of 1 ohm. Okay. So if you have a total resistance of 1 ohm, according to Ohm's law, if you apply 1 volt across that, what will be the current that is flowing? IR is equal to V, right?
Yes, sir.
Yeah. So from the current value and the voltage value, we can predict what is R value, correct?
Yes, sir.
But higher the R, lower will be the current that is flowing, correct? Because it is impeding the flow of charge, correct?
Yes, sir.
So therefore, your voltage that you measure across the terminal between the photoanode and the counter electrode, okay,
Yes,
some
yes,
voltage is already dropped internally into the cell, because inside the cell you have a TiO2 making connection with the ITO, and there's an electrolyte in that. Ions has to move. For movement of ions, you need to spend energy. So all that energy will be considered as a voltage loss.
Yes, sir.
Okay. So that loss will not be an electrical energy, that will go as a heat. Okay.
Yes,
therefore, the voltage will not trace this red line. It will trace this blue line. At
Yes,
every voltage, there is a certain amount of current comes, but when the current increases, the IR drop, I into R, voltage drop will increases, right? So therefore, you have a curve like this, right?
Okay.
It's
Okay.
not
Okay.
any.
Okay. So same phenomena like that internal resistance what we used to study in primary batteries.
Yeah, same thing.
Yes, sir. Yes, sir.
Same thing.
Sir,
Any electrical device you take, there'll be internal resistance, and then there's a load resistance and so on.
Yes,
Load resistance deliberately we introduce to do the
Yes.
electrical work, but internal resistance, even though we want, we will not be able to remove beyond certain extent. Yeah.
Yes, sir. So my second question is, so can we fabricate dye-sensing solar cell that is solid state dye-sensing solar cell by using N719 dye? Because I could not see the papers which is related to solid state dye-sensing solar cell using N71 dye.
Can you repeat your question, please?
Sir, is it possible to fabricate solid state dye-sensing solar cell using N719 dye?
Any dye you can use, no problem.
But we have to choose the electrolyte according to that.
Not necessary. As long as you know your electrolyte redox energy is just above the HOMO of your dye.
Yes, sir.
Okay. So if you are fixed with for example, if you are fixing the electrolyte, then you have to choose dyes such that their HOMO is below the redox energy of the electrolyte.
Yes,
if you have fixed the dye, then you have to choose the electrolyte such that the redox energy is above the HOMO. Either way.
Yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you very much.
Please, participants, please unmute yourself and ask your questions.
Sir, if we use a combination of dyes, is it possible to go beyond the Shockley-Queisser limit or the efficiency limit?
Still not possible. The reason why, you can improve, but not 100%. The reason why, even if you have a dye, for example, this gray area, okay? So the band gap of your dye is such that this is not for a dye, this is for single crystal silicon, but I just extrapolate here. Imagine instead of silicon, you have a dye here. So the dye has a band gap such that it can absorb light between the 500 to say 1000 nanometer, okay?
Okay.
Clear? But we may not have enough dye that can absorb all the light which is available, all the photons which is available in this region, correct? So then what will happen? These are the, see, whatever that shows in blue, I mean yellow, that region just above this gray, there are total yellow, but you subtract from that this gray region, then you get the remaining yellow region that is here. Okay. So that much of light, even though dye is capable of absorbing, will not be used because you are having dye in limited quantity than the photons. Therefore, you will be losing this energy, even though you have made a dye which is, therefore, that's why I said you should have enough dye concentration also. That is important. Otherwise, this region, this gray region will shrink if you are decreasing the dye loading. Okay. So no way that you will make, because of the practical limitations of you can't only load so much of dye and you can only catch only so much of the spectrum. These two reasons, and in addition to the back electron transfer, these three reasons will limit your Quasier limit. I mean, set to this Shockley Quasier limit. Okay. So, but not necessary, it will be 30%, you can increase to say 40%, possible, but not to 100%. Yeah.
Okay, sir.
If you want to make it 100%, you should have a situation where this gray is exactly overlapping on this yellow without any back electron transfer.
So what if we trap the energy loss which is as heat, if we use a thermoelectric material, how feasible is it to reuse that heat energy which is lost?
Okay, thermoelectric and all is fascinating. You can't use it here, I believe, because you are having a glass plates on both sides or polymer plates on both sides, correct?
Yes, sir.
They are superconductors of heat. So heat that is produced inside will not even come out. Yeah.
Okay.
Then how will you use your thermoelectric on that? Until unless you inbuilt that into the device, and that calls for a lot of material qualification and understanding. Yeah.
Okay.
Okay, sir, we have few questions in chat box also.
Yeah.
Mr. Manoj Kumar Malik is saying, sir, can you please clarify which parameters affect the fill factor of DSSC and can we improve it?
Yeah, you can improve fill factor provided you reduce your internal resistance. And
he's asking for the parameters.
The parameters is that the internal resistance only makes this curve bend like this, right? So if your internal resistance is, if you reduce it, okay, then also your other over potentials, for example, the back electron transfer process, if you reduce that, then there will be, so imagine, let us choose one voltage, yeah, 600 millivolt, okay? Imagine at 600 millivolt, if there is suddenly no back electron transfer, okay? Then what could have happened? Instead of here, the curve could have raised a little bit, correct? That means you have got little more current at that voltage, correct? Likewise, in every voltage, if the current goes a little bit up, what will happen? You will start tracing area which is very similar to the red square area, correct? That means your fill factor will go to 1. That means perfect. Yeah. So for that, what you need to do? There are several things you have to do. One is you have to decrease the internal resistance and decrease the resistance in the circuits, and also the back electron transfer. So all that if you do, yes, it is possible to take the fill factor to 1. So it's all in the engineering, the way you engineer the device. Yeah. The problem is ITO, because you want a transparent plate. That's why we are using ITO. Otherwise, you can use copper plate or some other metal plate through which light cannot penetrate. So because we are using ITO, ITO has got a higher resistance, much higher than your copper plate, correct? So you have huge heat resistance. That is only creating a large internal, resistance contribution. Therefore, you will be never ever able to make, this blue line coinciding with the red line. Provided you can do that, provided you make some material which is transparent and as conducting as copper or silver or something, then yes, it is possible.
Okay,
that's why if you see the solar panels, there will be some silver lines every 2 millimeter or 3 millimeter gap. Have you seen that?
Yes.
Basically, they put those lines, the total area occupied by those lines is minuscule compared to the total area of your panel. Okay, right? So when you have those minute lines, what they do, they are basically silver lines. Those silver lines improve the heat resistance, decrease the heat resistance of your plate, because it is capturing the current in a very shorter region and then transport it outside. Okay, so that is why it is.
Okay, so one last question we have.
That is one way by which fill factor is improved for a silicon solar cell. Yeah, go ahead.
Okay, sir. Thank you, sir. There is one more last question we have. What is the morphological difference when you anneal film in a hot plate versus hot air gun? Does it have any role in power conversion efficiency?
If the morphology changes, definitely it will have. Upfront, I cannot comment except that there will be a change. Yeah.
Okay.
So, and when you put the hot air gun, it is applying a force on your surface, correct? So initially, your that paste will be like a semi-solid. So if your gun throws air very fast, what will happen is you will have some kind of coffee ring effect. Have you seen coffee ring? No, that Nora is there, no, in the coffee. So when you blow, it goes to the sides and form a ring.
Yeah.
Like the TiO2 all will go to the brim and form a ring. in the plate.
Oh,
Then you will not have uniform thickness, then it will not perform well. So better to heat uniformly instead of inhomogeneous heating. Yeah.
yes, sir. Yes. Okay, sir. Now I'll hand over this session to Dr. Asha.
Yeah.
Thank you, Dr. Shakila. Professor, thank you so much for the wonderful session.
I'm glad there were many questions, interesting students.
Hello, Professor.
Yes, sir.
Okay, thank you for your elaborate and informative lecture. Even the participants also interacted very nicely. Okay, thank you, sir. Thank you.
Sir. Nice meeting you, sir. Yeah.
Thank you,
Welcome,
Professor.
sir.
I know that you are very busy, but once I have requested you for this invited talk, without hesitation, you have accepted the request immediately. Thank you so much, Professor. Thanks for joining with us. I'll talk to you later, Professor. Thank you so much.
Sure. Yeah. I hope your talk is tomorrow, right?
Yes, Professor.
I'm sorry I stole a little bit content from your talk, but you will elaborate.
Yours is in a different dimension, Professor.
Okay, then. Yeah. All of you, good luck and spend your time usefully in the quarantine, in this pandemic time. Don't venture out unnecessarily.
Thank you, Professor. So
Thank
kind
you,
of
sir. Thank you very much.
So, dear participants, this is for your information. Tomorrow is the final day of our webinar series on photovoltaics in 360. So, tomorrow's session will be chaired by Dr. Rafiq Rajak Sheikh, Assistant Professor of our chemistry, and the moderator is Dr. M. Vajraved, Assistant Professor Senior Grade of our department. So, the myself is going to present. I hope I'll try to fulfill the expectations from the participants, and the details related to the quiz and regarding the participation certificate and all will be given in the tomorrow session. And thank you all. Thanks for joining. We'll meet you in the last day's session tomorrow at 4:15 sharp. Thank you.